Hello everybody, I will start my today another web coding session. Let's answer this question. Lowest common ancestor of a binary tree. Given a binary tree, find the lowest common ancestor of two given nodes in the tree. According to the definition of lowest common ancestor of Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendant, where we allow node to be a descendant of itself. Okay, I see. So I can think that if there is a node, I can think that that node is the descendant of that node itself, as it's written. Good. Okay, so let me start with the clarification. So as the interface, I'm given the binary tree as the root node. And also I will be given two nodes. So node 1, which is node, and node 2, which is also node. And what I will return is the lowest common ancestor node, which is node. Okay. So node 1 and node Q is the node in the given tree. So node 1 and node 2 always exist in the given tree. Yeah. So that being said, when I think of the constraint, I'm wondering if root and node 1, node 2 can be none or not. I will take a look. Number of the nodes in the tree is in the range 2 to 10 to the 5. Yeah. So I can say this, which means that root is not none. Or node 1 and node Q, node 2, they always exist in the tree, and node P is not node Q. Yep. Even if node 1 is equal to node 2, I should return node 1, which is the exact same node, because the node itself is the descendant of that node. The lowest common ancestor should be that node. But anyway, this doesn't happen. Okay, good. So let me think of this question with an example. So it says at least one, at least two nodes. So it looks like this, at least. So let's say this is P and this is Q. In this case, I should return node 1, which is equal to P in this case. Node 1 is the ancestor of node 2, yes. And node Q, yes. And node 1 is the ancestor of node P, because the node is the ascendant. Node P is the descendant of node 1, which is itself. I should return this one. Or let's say if the tree looks like this, in that case, I should return node 1. Yeah. Okay. Aside from that, the case I have to take care is, yeah, maybe P and Q should be swapped. In that case, that's the same. Maybe this is trivial example, but yeah, this is something I can say. So I can say there are three cases. Number one, P actually is the ascendant node of node Q, so I should return node P. This is case 1. Case 2, node Q is the ascendant of node P, so I should return P. Sorry, Q. And case 3, node 2 is not the ascendant of node 3, right, node P is not descendant of node Q, and vice versa. So I should find the parent node. Yeah. So let me start with brute force approach. The brute force approach is I take a look at each node and I will think if that node is the lowest common ancestor or not. So yeah. Oh, actually, I'd like to say one more thing in the example. So this has to be lowest common ancestor. So even though, let's say, like in this case, node 0 is also the ancestor, but I shouldn't return node 0, but node 1, which is the lowest common one. Yeah. That being said, I can say from the upper node, check if it is common ancestor, and if it is true, I return that node. So here I have to do the DFS to decide the upper node. And then again, to check if it is a common ancestor, I have to do the DFS for the subtree whose root is the current node. So I have to do the DFS twice. They should be take n squared time complexity. Yeah. But definitely I can optimize this. So the idea I have in my mind is using the recursion. So what I should return is I will return from each node if that node includes P. And also in each node, I return if that subtree includes includes Q inside of it, I return these two booleans. Yeah. And let's say in this case, this is the interface of the recursive function, and I will return the boolean has P and has Q. So this should return true false. This should return false true. So here in this node, I can say I have the P node as the child and also Q node as the child. So I can find this node 1 to be the common ancestor. And I do the recursion. So I do this check from the lowest node first. So the first node I find as the common ancestor is the lowest one. The first common node found first. Okay. Good. So this is it. Quickly, I will take a look at this case. In this case, this should return true and false. But here, this should return true, true, yes. But at this node, I have to check this is true. And also I will check this node itself is Q. Yeah. So check child result. And also the node itself. Yeah. And if I return true, true, which means that I've found the node. So this is the basic idea. Okay, that being said, let me start the implementation. Oh, by the way, time complexity. This should take O(n) time. Yeah, because I have to visit each node once as a recursive function in the worst case. Actually, the worst case is that the lowest common ancestor is the root node. In that case, I have to check each node in the recursive function. It takes O(n) time. For space complexity, what I have to keep track is the only, recursion stack, which is non-constant space data structure. So it takes O(n). So this is the case when the tree looks like a linked list, and I have to keep going down and down, and the depth of the recursion stack should be exactly n. So this is worst case space complexity. Good. That being said, I start the implementation. So I actually would like to do two things in this recursive function. So number one, return the tuple of Boolean, which is has P and has Q tuple. And also update self.found, or it's just the LCA if found. Yep. So being said, I call this function. Then I return the self.found. I should definitely find the lowest common ancestor because of the constraint. Yep. So now I will implement the helper method. So the first thing I have to take care is the base case. So if root is none, obviously this doesn't include P nor Q. So return false for. Good. Otherwise, if there is a node, first thing I will do is call the recursive function with the child node. And also I call it with this way. Okay. And also, as I said, I have to take care if the node itself is pure Q. Oh, so I have to keep track of P and Q. Okay. Okay, so now I've got the left as B, left as Q, right as B or Q, root. So has P is this or this or this. Same for has Q. Yep. So now I can say if both of them are met, I update the self.found is the root node. And also I have to update only for the first time. First time I find the, you know, find it, I should update. But otherwise I shouldn't update it. Because it is the common ancestor, but not the lowest one. Yep. Okay, this is it. So now let me walk through my code. Like as I said, I will check these 3 cases, but for saving my time, I do this one first and maybe this one too. Oh no, sorry. Let me just test this one. So here, let's say, this case, self.p is b, self.q is q, and self.found is none. And I call has p or q with the root node. Then inside of it, root is not none because I'm here. And let us be right as q is self.has p or q with the left node, right node. So for the left node, I have to check this one. But for the right node, it should be false and false because rooted right is none. And root is p, root is q. This is non-none. With this one, I don't know yet. So I have to take a look at this. And again, for this one, I call the recursive function. And I call this and this. So has period q1. I don't know, but this code has period q2 and 3. And also check self. So I would say as p or q of node 2, I'm here. So this node itself is p. So this should be, root is p should be true with this node, but root is q is false. And also these two right 95 to 96 variables should be false. So in the end, I end up that has p is equal to true. So I don't update the self.found, but return true false. And in the same way, this should return false true. So, and what happens is that here has period q node 1. Root is p, root is q is false, false. But has p, has q are true and true because I do take the OR of these 3. So now I can say has p and has q is true. So self.found is still none. So update it with node 1. Yeah. Then I return true, true. So what happens is that in the root node here, root node 0, left as p is true. And also left has q, this is also true. So has p and has q are true. But self.found is not known anymore, so self.found is not updated, and I return true, true. Yeah. So that being said, node 1 is returned. So this is as expected. So I passed this test case. Okay, so I covered those lines basically. So I'm pretty confident in my code. So let me submit. Good. And I submit. Okay, great. Accepted. Okay, so let me quickly wrap up. So today I saw the question, lowest common ancestor of binary tree. And in this question, I used recursion. So my task was I mean, was that I'm given the binary tree, and also I'm given node P and node Q, and my task was to find the lowest common ancestor. So for this question, I use the recursion. So basically, that recursive function does two things. Number one, return include P in that subtree Boolean, and also it should return the Boolean which represent if the subtree includes node Q. So those, tuple of booleans should be returned. And also, if the recursive function finds out that the root node, which is the argument, is exactly the lowest common ancestor, I update the global variable self.found. Yeah, if it is turned on. So basically, I do two things in this recursive function. And in the end, after traversing of the nodes, I can find the lowest common ancestor as self.found. A small optimization I can make is if one self.found is known, I don't have to call the recursive function anymore. So maybe here in the beginning of the method, I can add something like if self.found is not known, return known and known tuple. Yeah, but actually this doesn't improve the worst time complexity, because in the worst case, in the end, I have to visit all the nodes with the recursion. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.